In this video, we will be discussing the System International units, also known as the metric units, as well as some of the prefixes that are used to simplify the writing of very large and very small numbers. SI stands for Système International, which is essentially French for the international system for our units of measure. There are 7 base units upon which all other can be derived. These are called the base units. This includes the meter, which is the unit of length, the kilogram, not gram, which is the basis for the unit of mass, seconds for time, Kelvin for temperature, amount of substance is the mole, electric current is the ampere, and luminosity, or the intensity of light, is the candela. Units like the liter are actually derived units. Liter itself is not a base unit. Instead, 1 liter is a cubic decimeter. So that is 1 liter is equal to a box that is 1 decimeter long by 1 decimeter wide by 1 decimeter high. So it is actually based on the meter. There are a variety of other derived units. These units are defined based on 1 or more of the standard units. Some of the ones that we will be using this semester and next semester are the Hertz, which is an inverse second. Newton, you'll be using that a lot in physics. That is a kilogram meter second squared. Then we have the Pascal, which is a Newton spread over a square meter, or in terms of the base units, kilogram per meter per second squared. Watt is based on kilogram meter squared per second cubed. Then you have Coulomb, which is a second times an ampere. Energy units are the joule is the primary unit for SI, which is essentially a kilogram meter squared per second squared. One unit that it gets used a lot is Celsius, although it is not the base unit, it is a derived unit. It is based on Kelvin. So as was discussed in a previous video, we can get Celsius from Kelvin by adding 273.15 to our value for Kelvin, and that gives us our value in Celsius. The standard value for concentration is molar, which is 1 mole per liter. There are a large number of other derived units that are defined based on our base units. One of the advantages of the metric and SI system of units is that it is on a base 10 system, which means scaling up and down go in multiples of 10, 100, or 1,000, the vast majority of which are in the order of 1,000. So going from a small unit like the centimeter to a large unit like the kilometer is fairly easy to do, whereas in the imperial system, going from something like an inch to a mile involves very complicated unit conversions. The way that the metric system does this in terms of going up and down in sizes is using prefixes in front of the unit. So for example, a centimeter is a meter which is modified by the prefix centi, and the number would be multiplied by 10 to the negative 2. So 1 centimeter is 10 to the negative 2 meters. Going up to a larger unit, kilo, here has the prefix of a k and has a value of 10 to the third. So 1 kilometer is 10 to the third meters. For this class, the ones that you will need to have memorized are the ones that are highlighted or denoted here, from tera down to kilo, and then centi down to femto. So essentially from 10 to the negative 15th up through 10 to the 12th are the ones that you will commonly see in your scientific careers. Some of the less commonly used ones are hecto, deca, and deci. The vast majority of the prefixes increase by a 10 to the third amount. So going from kilo to mega, the value that you are multiplying your given numerical value by goes from 10 to the third to 10 to the sixth. Giga is 10 to the ninth, and tera is 10 to the 12th. So essentially, if you have a terameter, for example, that would be 1 trillion meters, or 10 to the 12th meters. A gigameter would be 10 to the 12th meters. A gigajoule would be 10 to the 9th joules. So in terms of memorizing things, one of the key things to keep in mind is that your units, with the exception of centi, are going to increase or decrease by factors of 3. 10 to the third, 10 to the sixth, 10 to the ninth, 10 to the 12th, 10 to the negative third, 10 to the negative sixth, 10 to the negative ninth, 10 to the negative 12th, 10 to the negative 15th. Centi is one that will be used fairly frequently in your scientific career that does not follow that standard factor of 3 increase or decrease. It is 10 to the negative 2. I will include it as one that you should memorize because it is used so often in science. An easy way to remember whether or not the prefix makes the number bigger or smaller is virtually any time that the symbol that gets used is a capital letter, it means that it is a larger value. So mega would be represented with a capital M, so like a megameter would be capital M, lowercase m. The lowercase m denotes meter. Capital M means mega. So that would be 10 to the sixth. The majority of the ones that are in lowercase are ones that make the value smaller. The exception to this is kilo, hecto, and deca. These are fairly older units or older uses, and so those are ones that sort of predate the larger values, which is why they're still in lowercase. In 2019, there was a significant change in how the units were being defined. Prior to this, the values were based on experimental setups, with the exception of the kilogram. After 2019, all the units became based on universal constants. So going back to our discussion of what makes a good unit is you need to have either an experiment that will produce the same results everywhere, or have it based on a universal constant. Having it based on a universal constant is better than having it defined based on an experiment. The reason for this is as experimental methods progress, you will introduce new, easier to use experimental methods. And so if it's instead of being defined based on a particular experimental method, but is instead based on a universal constant, as your experimental technique improves, you can probe the universal constant without having to rely on a less accurate method. So prior to 2019, the meter was based on the speed of light. The kilogram was still actually based on a physical object that was held in a museum in France under several layers of glass and vacuum. It was a palladium composite metal, and the reason that this particular composition was used is because it was fairly non-reactive. The problem with having a physical object as the basis of your definition is, well, there are several of them. One could be, as you're handling it, if someone were to, for example, touch it with their finger and get some finger oils on it, it would actually change the unit of measure. It would now weigh more, but because all weight is based on the physical object, your scaling of the weights would change. Or if you scraped some of the metal off, then it would weigh less, but because it is the basis for your definition of weight, everything else in the world would instantly have a larger unit for the weight. So this creates some problems. A good website for looking at units is from the NIST, the National Institute of Standards and Technology, which has a good explanation of the various units. Now, in 2019, there was a redefinition of all of the base units. All the base units are now defined based on universal constants. So the second is still based on the hyperfine transitions for a cesium atom, but the rest of the units are based on universal constants. So for example, the kilogram is based on Planck's constant. The mole is now based on Avogadro's number, so we have defined Avogadro's number as being exactly 6.0221486, as opposed to the previous definition for a mole, which was the number of atoms in a 12-gram sample of carbon-12. The meter is based on the speed of light, and K, your temperature of Kelvin, is no longer based on absolute zero and the triple point, but instead Kelvin is now based on Boltzmann's constant. The advantage of doing this switch again is as our experimental techniques improve, we'll be better able to further refine the universal constant, but because all of our measurements are based on the universal constant, it will be easier for us to be able to use the various units. The change in the units didn't actually have a noticeable effect to the general population because the values for the universal constants were defined based on the pre-existing value. So Planck's constant itself was set to be this exact value, which would give a kilogram to weigh the same amount as the physical object of the kilogram. But now that they're based on universal constants, it will be the same no matter where you go.